Okay, so hello, my name is Ayumi Akimoto. Today, I will present a novel approach to completing street tree surveys using Google Street View. So planting more trees and having more green spaces are encouraged more than ever in cities. A very good movement with potential local as well as worldwide advantages, including mitigation of climate change. Integral to the success of achieving these benefits is that the trees remain healthy, and street tree surveys are an important method of assessing tree health, and the data collected helps with planning and budgeting by city governments. So the way typical street tree surveys work is for surveyors to go visit the individual tree site. The observer will observe individual trees and complete data sheets and then move on to the next tree. The Google Street View survey is almost identical, except that the tree site is visited virtually. So this eliminates the travel time, resulting in a significant time and cost saving over the traditional surveys. There are advantages to each type of study. On-the-ground survey allows the observer to see more detail, while for GSV, fewer man-hours are needed, transportation to the sites is eliminated. And most importantly, the surveyor can look back in time to observe the same tree site many times over a 10-year period, while the conventional survey would only observe the tree once in that same 10 years for most cities, including the city of Toronto. So the overall objective is to our study to evaluate the potential of doing street tree survey is using Google Street View. Maybe you can see better. And in order to do this, we must first have a protocol to follow to ensure a high quality data set is collected. Complete a pilot study of street tree mortality in the city of Toronto, and analyze the data and discuss the results, including evaluating consistency in observation between observers and also problems found with the survey protocol. We will then suggest some ideas for future studies using Google Street View. So what does an observer see when doing a GSV survey? This is a good example of what an observer would see using GSV to look back in time at one location. So this actual tree site within the city of Toronto captures the death of a tree at this location. Note that in 2014, there are newly planted trees at this site that appear healthy, but in 2015, this exact same tree is clearly unhealthy. And in 2017, it's completely missing. So GSV is a helpful tool to catch such events and approximately when it happened. And because the use of GSV is a relatively new method, it requires training of surveyors. Identifying trees in GSV is quite different than in person. So we created a GSV street tree ID training document, which contains 13 common street trees in Toronto. This is one of the pages in the document to give you an idea of what a surveyor would see during training. The goal for this document is to have surveyors accurately identify street tree and thus provide consistency in the tree ID dataset. Identifying trees from GSV images can be very difficult because they are often blurry, making it hard to see important diagnostic features. So this training document is built around that limitation and attempts to use ID features that are at a larger scale. So it's essential that tree locations are picked randomly to ensure that the relatively small number of trees surveyed will represent the entire tree population within the city of Toronto boundary. A shapefile of Toronto's boundary was imported into all the random locations were uploaded within that polygon. So when you actually start the survey, a strict protocol is followed to minimize observer bias and to be consistent in the data collected at each site. So this is an example of the data collection sheet we used. Surveyors will fill out information like tree location, environment, type of neighborhoods, and DBH estimate and tree ID. This red circle highlights the clickable links to take the surveyor directly to the first GSV photo for the random location. As an example, if I click on this first URL, this is what the surveyor would see. So this street view photo shows this particular tree site in 2009. Note that the links take you to this tree in the year of 2009, the start of our survey. It's important to start with the live tree in 2009 at each site rather than start with a live tree in 2019 and work back in time in order to avoid biasing the results by preferentially picking trees that survived. So if I click on this history where the red circle is, I can see the exact same site in 2019. In this case, that tree we saw in the 2009 view is no longer here. It died and was removed and replaced by this tree. You can see that each white dot on this timeline represents a different year available, allowing the observer to step through and see when that 2009 tree disappeared. And this next section is of the data sheet is where events are logged. For each year, surveyors note whether the tree is alive, dead, missing, or replaced. For all the years GSV photos are available. For the example photo I just showed, it turned out the event happened in 2017, where this M means missing and then was replaced in 2019, shown by this arrow. And then on the very right is where tree species is reported. For example, the original tree was elm, but the replaced tree was honey locust. So with that initial work, we were able to complete our pilot study. While this was the small study with just 2 observers and 100 tree sites, it provided important information about how to improve the survey. Here I show the consistency of tree ID between observers. As can be seen in this table, the tree ID match at genus level was significantly higher than at the species level, which is 83% and then 60.7%. I also included the data from the only study of tree ID consistency, Berland and Lang 2017, which got similar results. But it's important to point out the Berland and Lang study compare GSV and field study, but it does give an indication that our results are reasonable. Tree ID consistency was lower for the less common street trees in the survey, which was also seen in the Berland and Lang study. This points out the need for observers to become familiar with less common trees and also shrub type trees that are often seen in suburban areas. So as with the tree ID comparison, we wanted to see how consistent the DBH size class data was between 2 observers. The red line is the 1-to-1 match. If both observers chose the same size interval for every tree, the data points are the actual data. And as you can see, some of them fall off this line. But note that for the points that do not fall in the exact match line, almost all of them are only 1 size class off. These were, so there was a 73% correct match between the observers, while 27% didn't match. However, we realized the DBH ranges we used overlapped, which could explain some of the mismatch. For instance, for the ranges 5 to 10 centimeters and 10 to 15 centimeters, it's possible for a match since 10 is included in both ranges. So if those overlaps are included in the calculation, then the percent of consistent results goes from 73% to 96%, a significant increase. So this illustrates the value of completing a pilot study, as this points out a potential problem for future surveys that needs to be addressed. So finally, we determine the consistency of what we call event identification. That is when a tree is dead, missing, or replaced. So of the 26 total mortality events identified, observers had an 85.7% match, showing in the left pie chart. While this is quite high, there are a few possible reasons for the mismatch of about 14% of the event years. After reviewing the observed tree locations from the pilot study, we can identify trees that were clearly dying but still had leaves 1 year and had no leaves on the next year. The question is which of those 2 years was the event. And in this case, the 2 observers chose different years. So this points out to the fact that future surveys should have a clear definition of dead. On the right is the success rate if the sites with these problems are removed, increasing the match to 96.4% and showing that if some of the protocol problems are fixed, the consistency for GSV data will be significantly improved. So we used the data we collected to determine an annual mortality rate by different variable. And on the first graph, this is showing now. Okay. This is the mortality rate and tree size class. The dotted horizontal line is the average annual mortality rate, which is 2.8%. This mortality rate is within the range of other street tree studies. And it was encouraging that Janelle's presentation yesterday shows the similar mortality rate. So looking at mortality rate by size class, 10 to 15 centimeters stands out with the highest mortality rate. Although the uncertainty in our study is rather large due to the small size of the data set, some interesting results like this can be seen and indicate further analysis is necessary to see if it's real or investigate the causes.
10-minute mark.
Thanks. So we then looked at the annual mortality rate by tree species. We picked 4 most common species to analyze. It appears that red oak mortality is significantly higher than the other species. It's not entirely clear why red oak has such high mortality, but again, it highlights the links to mortality that should be investigated. And the third analysis we did was mortality rate by year. Mortality rate for each year observed can give an idea if there are any extreme events such as weather or invasion by pest. In our data, it can be seen that mortality rate in 2013 is significantly higher than the other years. It's not possible to know for sure whether this is a real or an artifact of the small data set, but it's interesting that in 2013, there were actually 2 extreme events in Toronto. One was a flooding event in July that was the most costly natural disaster in Ontario history. And the second and possibly most likely cause of high mortality was an ice storm in December of that same year. So if we analyze the statistical significance of our results on these 3 observations using simple chi-square test, it shows that the size class does not appear to have an effect on annual mortality rate, but both species and year are at statistically significant levels. The most important conclusion from the study is that Google Street View has the potential to be a valuable tool for street tree surveys. We believe the data consistency is likely to be very good if the problems identified in the pilot study are addressed in the future studies. The mortality rate calculated from our small pilot study is within the range of previous studies, although with a large uncertainty. So some important information came from the process of setting up the GSV survey and problems identified with the pilot study. Correcting these problems before a large study is undertaken will save time and increase the chance of success. So some of the points to be addressed in the future include the protocol must be very detailed and precise in order to provide consistency among observers. Techniques for better tree identification should be investigated to improve the value of GSV. A larger study is necessary to confirm the results presented here, as this was a relatively small study with only 2 observers. In future studies, thank you. Future studies should assess the usefulness of monitoring the health of newly planted trees over the first 5 years, as they are most vulnerable during that time. And other applications for specific surveys, such as invasive species and pest problems, should be investigated as well. So I would like to thank Anna, Annie, and Joy for helping with some of the initial work on the street tree ID document, and Halim for helping with the oral to get the random sampling location, and Wenxi for Melanie for giving me a feedback on my presentation. And I would like thank Amory for being my external examiner, and my Capstone advisor, Sean, who helped a lot with the statistical analysis. Thank you.
That's great. Thank you very much, Ayumi. Interesting presentation.